All right, today we are going to continue our journey through equilibrium chemistry. I wanted to kind of show you where we've been. We did 7.1, 7.2, and 7.3. You turned that one in on Monday. And then we did this little segment also as an assessment that is due tomorrow by 9:10 a.m. And today we're going to do 7.7, big idea. So let's go ahead and go to the slideshow for this one, and it's calculating equilibrium constants, but at a little bit higher level. And I think you're going to see what I mean today. Brand new tool that we're going to teach you that is very, very beneficial in doing problems like this. So here you have some gaseous water. Okay, so it's water vapor, and it's at 25 degrees Celsius. The pressure is recorded to be 0.7842, so that's a little less than 1 atmosphere. And then what are going to be the partial pressures of each species when it reaches equilibrium? Okay, well, that's a reaction that you know intuitively is not going to happen very much, right? Water vapor in the air doesn't turn into explosive hydrogen gas, thankfully, with a little extra oxygen to give it that extra kick. So that does not happen spontaneously. And as is indicated by the equilibrium constant here being extremely small. I don't know if you've ever seen a number that small, 10 to the minus 42nd. So it really, really favors staying in the water form. And again, thankfully. All right? So notice we have Kp. So you start thinking, well, parentheses and partial pressures. Kp. So here's where the new stuff comes in. I had a nice little song about Ice Baby, but I don't want to sing it because then YouTube will shut me down again. I'm already on their most wanted list, so I have to be careful about that. So anyway, we've got this nice little balanced equation up here. Even though these are partial pressures, I would recommend not doing this step. Excuse me. I think putting the actual balanced chemical equation in the top part of one of these ice charts. Now, I like to call them an ice box because it makes me think of food, like a refrigerator. But you can call it an ice chart, ice box. So we use this little acronym ICE, I-C-E, which will prove to be very helpful in doing these problems. So you start off with 100% water, and then you let the reaction occur. So the initial conditions, when you start with, sometimes you inject a little hydrogen gas and a little oxygen gas and let that reach equilibrium. But in this case, we started with just water vapor. So these initial partial pressures are 0 atmospheres. And remember, ATM is usually our go-to with partial pressures unless told otherwise. And then it's just a little conversion. Now, this is the change. Well, if you look at the balanced chemical equation, that's going to help you. I like to think of C representing two things. Change is good because it does change. This is going to be a minus because some of this is going to go away, and both of these guys will be plus as new product is formed. However, I like to think of C as also standing for coefficient in the balanced chemical equation, because these are in a 2 to 2 to 1 molar ratio. So what we're going to do is we're going to use X as a variable, and we'll say this water will disappear by 2x. And that's because of the coefficient in the balanced equation. This will increase at a rate of 2x because it's a 2-to-1 ratio over here. And this one will increase at a rate of x. All right? And then, at equilibrium, you simply go, well, this started at this, and 2x was taken away from it. So 0.784 minus 2x, and of course 0 plus 2x is 2x, 0 plus x is x. So now you've got all the unknowns of what the equilibrium concentration will be. And we can go to the next step. Remember, partial pressure equals parentheses. So go ahead and write the Kp expression for this guy, just to make sure that you've got this all down. Hit the pause if you need to. And sure enough, Kp equals, did you remember to write the little p sub h2? Got to hammer that home, okay? Very important, that partial pressure, that's how you write it. And that, of course, is squared because of that 2. Partial pressure of the oxygen, no coefficient. Here, partial pressure of the water vapor. These are all gases, so you've got to include them all. And now, all you have to do is substitute those x's into the equation. So, there's a lot here, so you might want to hit pause so that you can pay attention to what I'm saying here. But you're just simply plugging in the values right here. And some people get a little bent out of shape about this. They say, well, you double it and square it? And the answer is, yeah, you do. All right? Because it's a 2 ratio. The square is just part of this equilibrium law expression where the coefficient becomes exponents. So you double it and square it. So as a result of that, when you simplify here, and this is just plugging in that really, really small Kp value that we gave, and remember, no units for these guys. A little bit of simple algebra there, and you get 4x3. And I like this little cheat that we can use here. It's very useful. If your equilibrium constant is small, less than 1 times 10 to the minus 4th, well, see how this is 3 places? If you have numbers that you're subtracting, remember, it's all about place value. And if you subtract 0.784 minus 0.000000, it's not going to have any effect because the place value will force you to round it to whatever that number is going to be. So this is not a piece of cake, but you did make it easier by getting this 2x out of there, and you avoided the old dun 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 dun, which apparently to a lot of Red Wing learners means the quadratic formula. You'll get a chance for that. Hang in there. We'll get a chance to do that coming up. Not today, but it's coming. So right now, if you have really small equilibrium constants, those are the ones we'll start you off with here. And lo and behold, you can just ignore that minus 2x and put that down there. And then, of course, you're still going to square the 0.784. So, this is really important that you communicate correctly with your calculator and you solve this for x. I think most of you, that should be kind of a piece of cake. Again, strongly recommend using the EE key, 2.0 EE negative 42 as you're solving the problem, and you multiply it by this squared, and you're going to have to do a cubed root function. So make sure that you know how to do all those things, and when you do that, you should get an x value of 6.7 times 10 to the minus 15th ATM. because it's partial pressure, remember. Let's go back. You had 2 sig figs in that number right there, so that's why you had to round your final answer to 2 sig figs. And don't get thrown off by, oh, that's just 1 sig fig. Nope, that's a number that has infinite significant figures, and these are all numbers, okay? The measurement is that guy and that guy. All right, so those are the ones you have to use for significant figures. So the oxygen, which remember we defined as being X in our ice baby chart, and box. So 6.7 times 10 to the minus 15th atmospheres. And then to figure out what the partial pressure of the hydrogen is going to be, remember, those guys were in a 2-to-1 ratio. So all you have to do is take 2, the number, not a measurement, so you still get to stick with 2 sig figs, and when you do that and round, you'll get 1.3 times 10 to the minus 14th atmospheres. All right? And that is definitely something that you can do. Oh, and then the partial pressure of the water is not going to change significantly according to what we have here. I mean, it would be 0.784, 0.0000000 something, but that's useless to write that because significant figures say you don't have to do that. So you can double check just to make sure your initial estimate was that really the X value needed to be less than 0.784, and it turns out with that small of a K value, yeah, it turned out to be that. So sometimes you get to this point and you're like, this will come out to be 1.3 times 10 to the minus 2, and then you've got some work to do. You've got to go back and use that quadratic formula. So just keep that in mind. But this one worked out real nice. It wouldn't change the denominator at all, so we made a very good assumption. And then this roughly should equal our value. Now notice this is 1.8 times 10 to the minus 42nd. Well, that's just, we did some pretty serious rounding there to 2 sig figs, and that is definitely in the ballpark there. Okay, so those are 2 little check things you can do at the end, just to make sure that you stayed on the right track when you're doing a problem like this. Okay, so that is a partial pressure problem with parentheses, and then this guy you will see is a concentration problem. So it's going to be a little bit different because they don't give you the concentration. So I see them at about 13 minutes. So we're going to do a second video, one on the partial pressure icebox, and this one will be on the concentration icebox, where we'll let you do a little bit more of it before we turn you loose to do the assignment, of which the answer key will be posted. So go to video 2 for 7.7 video 2 at this time. Bye.